everybody, and welcome to our video on derivatives as rates of change and how we can apply derivatives to rectilinear particle motion. First, let's review some things that we already know about the first and second derivative and how they relate to particle motion. So first of all, we know that the derivative is a rate of change. We also have learned that the velocity is the rate of change of position with time. We also know that the acceleration is the rate of change of velocity with time. So if we're given the position function s of t, we can easily find v of t and a of t using the differentiation rules that we now know how to use. So we'll mainly be using the power rule in the functions in this section here. When we talk about rectilinear particle motion, we're talking about an object moving in a straight line, like on a track or on a number line. The wording and the context of the problem indicate which direction is positive and which direction is negative, like north positive, south negative, or east positive, west negative. It just depends on the context of the problem. But our particle is moving along a number line, one dimension. So our starting point is its zero position. So when we talk about a number line, for instance, we can say here's 0. So our particle can move to the right, and it can turn around and move to the left, and it can move to the right again and to the left. It can go back and forth like that, but it's only going one-dimensional. So distance traveled is the total distance the object moves, considering all movement is positive. Meaning if I started here, where I started out at 0, and I went back and forth, back and forth, back and forth, and I ended up over here, I would want to add up all those back and forth lengths there to figure out how far I actually drove or walked or whatever it is. That's your distance traveled, the total distance the object moved. All right, so you don't have a sign when you're talking about distance. Distance does not have a sign. Displacement is different. Displacement is a vector quantity, which means it has a magnitude and it also has a direction. So displacement has a sign. So what displacement indicates is if you end up here and you started out here, technically you've only displaced this much distance right here from your starting point to your ending point, regardless of all of this back and forth movement. So when you talk about displacement, you're interested in how far you are away from the starting point when you stop. All right, so if you're on the left of the starting point, it would be a negative displacement in my picture. This would be negative displacement. If you ended up on the right side of the starting point, in my picture, it would be positive displacement. If your number line was oriented north-south, and this was your starting point, if you ended up north of the starting point, positive displacement. If you ended up south of the starting point, negative displacement. So it's a very important distinction here. Distance does not have a sign. However, displacement has a sign because displacement is what we call a vector quantity. And those of you who were in pre-calculus might remember some of this. So velocity is a vector quantity. Velocity has a sign. The sign indicates whether you're moving in the positive or the negative direction on the number line. So if you have any non-zero velocity, whether it's positive or negative, it indicates that the position is changing. So your velocity can be calculated by taking the displacement divided by the change in time. And like I said, velocity will have a sign, whether it's positive or negative. Speed, on the other hand, is not a vector quantity, so speed will not have a sign. Speed is the distance traveled, which is an absolute value, divided by the change in time over which that distance traveled occurred. And then we have acceleration. Acceleration is a vector quantity, so that means it's a signed quantity. Acceleration has a sign. Non-zero acceleration indicates that the velocity is changing. So if you have a zero acceleration, that indicates that you have a constant velocity. A few more things we need to know. So when the velocity is zero, this indicates the instant in time when the particle is changing directions. When the acceleration is equal to zero, this indicates the instant in time when the velocity is changing directions. So taking these two things together, we can address these questions here. When is the particle speeding up? When is the particle slowing down? And when is the particle have a constant velocity? So when a particle is speeding up, its velocity and acceleration both have the same sign, which means they're acting in the same direction. So when the particle is slowing down, the acceleration and the velocity are opposing one another. They're acting in opposite directions, and they will have different signs. So if you have a constant velocity, then the acceleration will be zero, indicating that your velocity is not changing. So we're going to use a table of signs method to determine over which time intervals the particle is speeding up or slowing down. So let's start out with the basics. So if you're given a position function here and you are asked to find the velocity and the acceleration functions, then we're going to just apply the power rule to differentiate the functions. So we'll start out by finding the velocity function, which is the derivative of the position function. So using the power rule, I'd say 3 times 6 is 18 t, and then I bring my power down by 1, so my power is 2. Now I say 2 times 81 is 162, so that's negative 162. And then I bring my power down by 1, so that's t to the first power, so I don't need to write my power. So the power here is 1. So if I differentiate 360t to the first power, I've got 1 times 360, and then I've got t to the 1 minus 1, which is t to the 0, which we don't write because that goes to 1. So this is my velocity function here. All right, and then to find the acceleration function, I differentiate the velocity function. I find the first derivative, and I'm going to use the power rule again. So my acceleration function, looking at my velocity function, 2 times 18, that would be 36. And drop my power down by 1, that would be t to the first power, so I don't have to write it. And then this is a first power here, so that would be negative 162 times 1. Drop my power down by 1, that makes it t to the 0, which is 1, so I don't have to write it. And then the derivative of a constant is 0, so I don't have to write that. So my acceleration function is this function here. We're also asked to find the time when the velocity is 0. So to do that, you're going to set your velocity function equal to 0 and solve it. So we're solving for t. So I have 18t squared minus 162t plus 360 is equal to 0. So if you can see that this has a GCF, you can divide out by the GCF and make your factoring simpler. So this is t squared minus 9t plus 20 is equal to 0. So that is factorable because I I've got 1 times 20, 2 times 10, and 4 times 5. 2 negatives would add to give me negative 9. So I've got t, negative 4, negative 5. Okay, if we have factors, we have solutions. So t is 4 and t is equal to 5. So these are the 2 times when velocity equals 0. So here I've got my velocity function, here my acceleration function, and my times where the velocity is 0. Next question says, which scenarios indicate a particle is speeding up, slowing down, or moving at a constant velocity? So here we can go back to our notes page here where we talked about if a particle is speeding up, its velocity and its acceleration are going to be acting in the same direction, either positive or negative. If the particle is slowing down, its velocity and its acceleration are going to be acting in opposite directions. So that's what we're going to look for. So A says positive velocity and positive acceleration. So those are both positive, so we're going to say this particle is speeding up. B says negative velocity and positive acceleration. Well, they're acting in opposite directions, so this particle is slowing down. C says negative velocity and negative acceleration. Those are acting in the same direction, so this particle is also speeding up. And D, positive velocity and 0 acceleration. Well, if you have 0 acceleration, that means your velocity is not changing. It's a constant velocity, so we can just say constant velocity. Okay, so those are the scenarios indicated by the signs of your velocity and your acceleration. In example 3, we're told that a particle is moving along a straight line north and south. So our number line is vertical. It moves 170 kilometers in 3 hours going south, 190 kilometers in 3 hours going north, and last 230 kilometers in 4 hours going south. So let's just draw a little picture. So we'd have a starting point. So this is your start. And then it says that first he's going 170 kilometers south. So down south, 170, over a span of 3 hours going south. And then it goes 190 kilometers over a span of 3 hours going north. So let's just make a schematic here. So now he's going to turn around and go past the starting point, and this time he's gone 190 kilometers over 3 hours again. So we must be going faster. And last, he moves 230 kilometers in 4 hours going south. So he's going to turn around and go past that point, because this piece here is 230 kilometers over the span of 4 hours. So finally, he ends up here. So imagine this is all happening on a straight line, or he's actually going up and down like this, but I just put this little dashed line here so I could draw these pieces separately. All right, so he starts here and he ends here. All right, so now let's answer some questions about this. Find the distance the particle traveled. All right, so here he is. He's walking, is whatever he's doing, moving. He's gone this far, and then this far, and then this far. So that means I have to add up all these distances. 170, he covered all this distance, plus 190, plus 230. And that's going to give you 590 kilometers. All right, so that's the distance traveled. Okay, so this is not a vector quantity, so no sign on that. All right, so now on the second bullet, we're asked to find the displacement. All right, so that's a different matter. We're trying to find how far he is from his starting point. This is your displacement right here. This is the displacement. How far did he get from the starting point? So he's south of the starting point, so we know that for sure. So in order to figure out the displacement, you're going to say you've got this negative quantity. So he went negative, and then he turned around and went positive by 190 here, and then he turned around and went negative again by 230. So if you combine all those numbers, take the sum there, you end up getting a negative number, which indicates that he's south of the starting point. All right, so there's an example problem. There's a homework problem that asks you not for the sign itself, but it wants you to put the direction indicator north or south. The way that you'd answer a question like this would be 210 kilometers south to indicate that you're winding up south of your starting point. And that's what that negative is telling you. All right, the next question said, find the average speed of the particle. So if we go back and look at our definitions page, speed is distance over change in time. So in order to calculate his speed, we want to take his distance and divide it by the time it took to cover that distance. So his distance is this number here, 590 kilometers. So I'm going to write my formula here, distance over time. So that's 590 kilometers divided by my time. So I've got 3 hours plus 3 hours plus 4 hours. That's 6 plus 4. That's 10 hours. So this is 59 kilometers per hour. And this is his average speed. All right, now for average velocity, back on that same formula page, velocity is a vector quantity. So we want our displacement quantity, which is a vector quantity. It has a sign, is what I'm getting at. Displacement over time. All right, so our displacement was this quantity here, 210 kilometers. And we know it was south. It's got that negative on it. It took the same amount of time to displace that much. So that ends up being 21. Let's put our units on here. That's 210 kilometers over 10 hours. Oops, just hours. Which is 21 kilometers per hour. All right, and this is acting south, negative. So I'm going to say 21 kilometers per hour south. So it depends on how your problem is worded, whether it's the sign, the negative, or the word south that the problem is asking you for. Just read the instructions carefully. Okay, so that covers that problem. Okay, this problem here says a particle is moving along a straight line. Its position function is given here, where t is in seconds and s is in feet. Then it says the domain of interest is time 0 to 7 seconds. So we're not interested in any times to the left or to the right. All right, so this question says find the position of the particle at t is equal to 0 and t is equal to 7 seconds. All right, so let's go ahead and do our work on a clean page. So I know in a problem like this, if I go ahead and read through the questions, that I'm going to need to know my velocity function and my acceleration function. All right, so these are the questions. Find the position of the particle, find the average rate of change of the particle, find the velocity of the object or particle, whatever it is, find the speed, find the acceleration. So I'm looking through here and I'm going to tell myself, first I know I'm going to need to differentiate position and then velocity. So I'm going to do that first. So there's a big empty white space on the bottom of this page of notes that you can do this on. So to find v of t, I'm going to differentiate s of t. So 3 times 16 is 48. Drop my power down by 1. So let me just remind you, we're using the power rule. Of course, these aren't the only kind of position functions that you could have. You could have sines or cosines or exponential functions, whatever they are, but we're right now just working with polynomials. So we're using the power rule to differentiate these functions. All right, so then we've got 2 times negative 63. Drop the power down by 1. So that's t to the first power, so I don't need to write it. And then I've got t to the first power, so 1 times 81. Drop the power down by 1. That would be t to the 0, which is 1, so I don't need to write that. Derivative of a constant is 0. All right, so now to find a of t, I'm going to differentiate v of t. So I've got 2 times 48, that's 96. And then I've got minus 126, t to the 0 power, which is 1, and the 81 here, derivative of a constant, is 0. All right, so I've got my 3 functions that I'm going to use for various steps in this problem now. So the first bullet says find the position of the particle at t is equal to 0 and t is equal to 7 seconds. So that simply means I'm going to plug in 0 for t and I'm going to plug in 7 for t. I'm going to find the position at those 2 times. All right, so s of 0 is equal to 16 times 0 cubed minus 63 times 0 squared plus 81 times 0 plus 1. So that's just equal to 1. S of 7 is 16 times 7 cubed minus 63 times 7 squared plus 81 times 7 plus 1. That comes out to be 2969. This is in feet. All right, so going back to our page, I filled that in. Okay, so the next question says find the average rate of change, delta S over delta T, over the interval 0 to 7. So we want the change in position, so that would be 2969 minus 1 divided by the change in time. We could probably fit that in here. Change in position over change in time. And going from 0 to 7 seconds, so 2969 minus 1, those are your 2 S values. And then we've got 7 minus 0. So that's 2968 divided by 7. So that comes out to be 424. So 424 feet per second. All right, so next we want to find the velocity of the object at t is equal to 7 seconds. So that means we're just going to substitute 7 into the velocity function. So v of 7 would be 48 7 squared minus 126 times 7 plus 81. And that comes out to be 1551 feet per second. And I'm just going to note that this is a vector quantity, so it's a positive number. So v of 7 is positive. So if it was negative, you'd be going in the negative direction. Okay, in this problem here, we're not told it's north or south, so it's either negative or positive would be how you describe direction for this particular problem. So you have to look at the context of the problem. If this turned out to be a negative velocity, you would have to have that negative on there. With a positive velocity, you could leave the positive sign off and it would be understood to be positive velocity. Okay, so I wrote that in there, positive velocity. And then the next part says find the speed of the object at 7 seconds. Okay, so what's going on here is that we're talking about what's the difference between speed and velocity. Well, you might remember that one is a vector quantity and one is not. One takes a sign and the other does not. The velocity takes the sign and the speed does not. So since there isn't going to be any difference in how this looks because it was positive for the velocity, this number is going to look the same. If this was a negative quantity, then this would be a positive quantity. All right, so that's my speed. Next, find the acceleration of the object at t is equal to 7 seconds. So that means I substitute 7 into the acceleration function. So a of 7. So 96 times 7 minus 126. And that gives you 546. And you have to be careful with your units of acceleration. They're feet per second squared or meters per second squared. So you're always going to have time squared in the denominator. So at 7 seconds, my acceleration is 546 feet per second squared. Now this is also a vector quantity. So we're going to note here that it's positive, but in some problems it might come out negative, and you would have to put the negative on there in this problem because it wasn't a north, south, east, west wording in the problem statement. All right, so I'm also going to indicate for the speed that you're going to say there is no sign on speed. So positive velocity, so far, positive acceleration. Okay, the last question says find the times when the object changed direction over the time interval 0 to 7. So this is when the velocity goes to 0. So we have to find those times where the velocity goes to 0. So v of t must be 0. So v of t, my velocity function, was 48t squared minus 126t plus 81. All right, so I want to factor that or use the quadratic formula, whichever it takes. So I could see that there's a common factor here, so I'm going to divide out by 3 here. Let's put equals 0 over here. I'm dividing everything by 3. All right, so I dropped the numbers down a little bit, but they're still kind of big. I'm going to go ahead and use quadratic formula here. All right, and you're going to get the same answer whether you factor or use quadratic formula. It's your choice. Okay, if it's factorable, you can factor. In any case, quadratic formula will always work. So I've got negative b plus or minus the square root of b squared minus 4ac divided by 2a. So that's 42 plus or minus. That turns out to be the square root of 36 divided by 32. So that's 42 plus or minus 6 divided by 32. So I've got 2 times there. So the first time comes out to be 3 over 2 seconds. And the second time, where the velocity goes to 0, reducing that comes out to be 9 over 8 seconds. So there were 2 times where this particle switches directions. Okay, so we're done with this problem. We've answered all of our questions. Okay, here's our final example here. It says a particle is moving along a straight line. This time it's going north and south. Its position function is given here. Make a sign table. Determine the following time intervals in interval notation. So we're going to figure out speeding up, slowing down, speeding up, moving south. So we're given directional words here to use instead of pluses and minuses. So you have to read your problem statement carefully to understand whether it's interested in a plus or a minus or a direction word. All right? So then speeding up, moving north, slowing down, moving south, and slowing down, moving north. So a problem like this, we would use a sign table. In order to create a sign table, we need S of t, V of t, and A of t. So we have S of t. So you can see that this is just going to take the power rule to differentiate it. So the first thing you're going to want to do is figure out V of t and A of t. So I'm going to take it to a clean page to do that. So here's my S of t function. Now I want to differentiate that to find V of t. Now please don't use a calculator for multiplying 3 times 1/3. All right, because if you ever have a quiz without a calculator, then you're not going to know how to do basic math. So 3 times 1/3 is 1. So this is 1 in the front. Drop my power down by 1. So I've got t squared. And then I've got 2 times 27 over 2. So the 2's cancel. So that's minus 27. Drop my power down by 1. So that's t to the first power. So I don't need to write the 1. All right, and then this term here, this is t to the first power. 1 times 152 is 152. Drop my power down by 1, so that would be t to the 0, which is 1. So I write only 152. And the last term is a constant. The derivative of a constant is 0. So this is my velocity function. Now we can figure out the acceleration function by differentiating the velocity function. So 2 times the number in front, that would just be 2. Drop the power down by 1, that's t to the first power. Then I've got power of 1, 1 times negative 27. Drop the power down to 0, which means t to the 0, which is 1, so I don't need to write it. And then the derivative of a constant is 0, so I don't write that. So this is my acceleration function, and this is my velocity function. Okay, the next thing we need to do when we're setting up a table of signs is we need to find V of t is equal to 0, the times when the velocity switches directions. So V of t, t squared, minus 27t plus 152 is equal to 0. So I went through and figured out that I can factor that. And I'm sure you guys are expert factors, but just in case, the two numbers were 8 and 19, two negatives. So t minus 8, t minus 19. So that means that t is equal to 8. It switches directions, the velocity, and t is equal to 19. The velocity switches directions. All right, next thing we do, we're working on our table of signs, is we figure out where the times are where the acceleration switches directions. So A of t is 2t minus 27, set equal to 0. T is equal to then 27 over 2, or you can write it as 13.5. So t is equal to 13.5. The acceleration switches directions. All right, so now we're ready to set up our table of signs. All right, so you start with a number line, and with particle motion, you don't have any any times to the left of 0. So this is my time number line. All right, so we say that our particle starts moving at time 0. This is the method. All right, and then on this number line, I'm going to indicate the times where the velocity goes to 0. These are the 2 times we calculated where the velocity goes to 0. And I'm going to put on here the time where the acceleration goes to 0 as well. And what this does is it allows me to divide up my intervals along these critical times. Okay, so this interval here is 0 to 8. Smooth brackets. Do not use square brackets for time intervals. And I'm writing my intervals in these columns. And it goes on to infinity in that direction. So it always starts at 0, but it can go on indefinitely to the right, to infinity. All right, now I want to set up a sign table where I want the signs of my velocity and I want the signs of my acceleration so that I can compare them. So I can pick any number between 0 and 8 in the first interval and plug it into velocity, which I'm not going to take the time to do that because you guys can do that, I'm sure. You just plug in any number between 0 and 8. Any number you choose, you'll find out that you're going to get a positive velocity. Then you pick a number between 8 and 13.5, like 10 or something, and you plug it in there and you should get a negative velocity because after all, we said here the velocity should change signs, and that's what we calculated it would happen at time is equal to 8. All right, we do not expect it to change signs here, so you can check that by putting in a number into the velocity function, and you should get negative as well. But we do expect it to change velocity to change signs on the other side of 19, so you could put in something like 20. If you substitute it in there, you're going to find out that you get a positive velocity. All right, so I've got the top line filled out, just substituting numbers in those intervals into my velocity function. All right, and while you're working this out, if you ended up with a positive and a minus in here, you've got a problem because you're only saying your velocity changes signs here on this side, plus minus or minus plus, and here. Okay, but we're not saying velocity should change here, so you made a mistake if you get a changeover between here and here. Go back and check it, right? All right, so now we're going to figure out the signs for the acceleration, doing it the same way. I'm going to take that number that I chose, whatever it is, now I'm going to plug it into the acceleration function. So my number turns out to be negative here by plugging in. So let's say I plugged in 10. I'm going to find out that I get a negative acceleration. And then I plugged in 15, and I got a positive acceleration. And then over here, I plugged in 20, and I got a positive acceleration. It doesn't matter which number you choose as long as it's in that interval. Now, once again, I want to look at this, and I'll say, I'm saying that my acceleration should change over across this line here, and I can see that it does. I'm not saying anything about acceleration from here to here changing, so these should be the same. And I'm not saying anything about acceleration changing over here to here. These two signs should be the same. All right, so I'm done. Now I can answer the questions. All right, so whenever you've got two different signs, like here and here, you're going to be slowing down. All right, and whenever you've got two of the same signs, you're going to be speeding up. So I've got my slowing down and my speeding up intervals identified. So now I'm just going to go back to my table that I had on my problem statement page and fill it in. Okay, so this first line here says the particle is speeding up. Now I found that it was speeding up in 2 intervals. So remember how we write that in interval notation? You put the U symbol in there. So 2 intervals, the particle's speeding up. And then I found that it was slowing down on 2 intervals as well. So I'm going to write it in this fashion. And then it says, when is the particle speeding up and moving south? So here, south means negative, north means positive, depending on your problem statement, how it wants it. So I look at the direction of my velocity to tell me which way I'm going. If I have a positive velocity, that means I'm going north in this problem. North is positive. So I'm moving north if I have a positive velocity, which also means you'd have a positive displacement. So I'm moving south if I have a negative velocity. Okay, so that sign on the velocity is going to tell you which direction you're speeding up or slowing down in. All right, so now I can go back and finish filling in that table. All right, and then let's see, where am I? Speeding up and moving north on the interval 19 to infinity, because the velocity was positive. And then I'm slowing down and moving south on the interval 3.5 to 19, because the velocity was negative on that interval. And then I'm slowing down and going north because the velocity was positive on that interval. All right, so that's how you do a sign table and what it tells you about the behavior of this particle in motion. That's all we're going to do in this section. So that should give you enough to get a good start on the homework problems. So let me know if you have any questions.